Everyone, January 23rd. Oh, so tired. I just finished working. I mean, the work, how should I put it? I don't like to leave the work at a certain state that the next day, if I pick it up, I will feel, I will forget stuff, or I will feel like, nah, I should have done it yesterday. So because of that, I usually push until I reach a certain stage, and reach a good state in whatever work I do. And sometimes that stage is quite non-trivial to reach. And just like today, it's non-trivial. It took me so long to get to that stage. Okay, so let's do this and go back to work on this. See what the hell happened to this thing. All right, pseudo-palindromic paths in a binary tree. Given a binary tree where no values are digit from 1 to 9, a path in the binary tree is said to be pseudo-palindromic if at least one permutation of the no values in the path is palindrome. One permutation. So everyone needs to be even except for one. Return the number of pseudo-palindromic paths going from the root node to the leaf node. So we have 2 is 2, 3, 3, and 2, 1, 1, right? Yeah. How many do we have? 10 to the 5th. So we want to know the total number of palindromic. So maybe what we can do is to keep, basically, maybe we need to do recursion, right? So start from here. We want to know, oh, hold on. It says start from the root, right? Go from the root down. Okay, so we just need a count of everything. Not really the count of everything, because it has each path, right? It has to be each path. Well, we can go through each path, right? We can go through each path, and as we go through, we keep track of the count, right? When we go down. But how do we keep track of the count, though? Well, what we can do is, because we have only 9, 1 to 9, so we probably can use bit mask again, right? So basically, as we go down, and each one, when we hit one, we just exclusive all 1, and we hit another time exclusive all 1. So as long as we hit even number of times, that value should be 0. But if we hit odd number of times, that will be 1. And when we reach the bottom, right? When we reach the bottom, we can just simply check how many 1s are in it, right? It should be 1, 1. And I think Python has a function called like a bit count number of 1. I don't remember. Python count bits. int.bit count. Yeah, we have a function for that. All right, let's take a look. No, that is not right. Because I did this already. Oh, jeez. All right, we're gonna say copy. Should be 24, right? It's 24. I don't know why it's 23. Actually, it will be important. Okay, so now what we do? What do we do here is we will, oh yeah, and notice this. I have an absolute path here. I'm not sure. Should we do absolute path or just relative path? No, I'll put absolute path right now. Okay, so what we need is a this DFS, right? So I have a node. It's gonna be optional tree node and current state. State is integer. This will return to me. This actually return nothing. Okay, and we need to have self dot res is 0. Okay, and if not node, right, I'll just return. If it is node, what do we do? If it is node, what we're gonna do is node. We have the previous state, right? Actually, not. That's actually not right. Well, now we keep this. We say if not node.left and not node.right, right? So this is we are at leave. Wow, actually I need to incorporate the state first. So we say new state, right? So say new state shall equal to state exclusive or one left shift node dot val. Right. So we are at leave, and now we're going to just check when a count. If new state dot bit count is equal to is small or equal to 1, then self dot res plus equal 1. Otherwise, we don't do anything. Okay. Else, if we're not at leave, then we will go DFS node.left new state and DFS node.right new state, and we are good. Right, and then we basically run DFS root state as 0, and then we return self.res. Okay, let's take a look at 17k. Oh. Is that right? I didn't run any edge cases. We just go for it. Ugh. What? And not support between built-in method. Built-in method? Oh, my bad. Forgot to. Oh my god. Yeah, it was a built-in method. All right, it looks promising. Let's run it. Okay. We're good. We're good. We're good. Actually, very fast. Yeah. So I think this week, right? This is like what the second problem with bit masking. Right, 1, 4, 5, 7. DFS to each leaf and keep track. Right, keep track of the parity of the nodes along the way. As long as we have at most one node, one value whose parity is odd, we have a valid, we have a pseudo palindromic path. Now to keep track, right, to keep track of the parity, you can use a bit mask, right, where each value, where the presence, right, where the presence of each value will be exclusive word, right, will be exclusive word. Thus, at the end, if a bit position, right? The bit position is 1. We know there has been odd number of occurrences of the number of the value. Let's call it value. Otherwise there has been even number of occurrences. So runtime, we have to go through everything. So it's on, right? We have to go through everything at least once. So we do on, and the state doesn't really matter. So I think that it's just on. And we have a pretty nice runtime. I can check before. I don't know why this one takes so long. Oh, path -1. That is smart. That is smart. That was smart. Bit mask was good. I think maybe the test cases, maybe the test case changed or something. I probably use a counter. Yeah, I was like, I think I probably use a counter. Okay, so that's that. Next, back to this problem. Oh. So the 1 1 2 2 1 1 2 2 4 5 5 8 8 10. How many? 1 2 3 4 5 6 7 8 9 10. 1 2 3 4 5 6 7 8 9 10. All right, so what I do, I sort it and I take away everything that's good, right? So it's a 10, so this one can be taken away. We don't have to worry about this. And it's 10. Well, 10 minus 1, 9. This is larger equal to yes. So n is equal to 9. Okay, n is equal to 9. Free is going to be 1. And then we have from 0 to 5. Right, 0 to 5. And total repetitions is from here all the way to here, which is actually I'm not even sure. And then expected 8. Let's do this. Expected 8. Okay, so what we want to do is I'll print total repetitions, and then I'll print mid, low, high, mid, and then required. Okay, and then we'll do the same thing. 36. That's the total is 36. And then oh, plus equal 1. That's not right. It's mid plus 1. You are kidding me, man. Ah, it's mid plus 1. I mean, still wrong, but but now we search it faster. Okay. Yeah, we're still not right. So we start 0 with 5. 5 we can do, right? And then we say next is 8. 8 we can do. And next is 9. 9. 9 we cannot do. 8 we can do. 9 we cannot do. Right? Because 9. So we can do 8. 8 is 36. Oh, 8 is 36. Hold a second. If we do 8, that is 36. 1, 2, 3, yeah, 36. So required total, right? Total rep is 36. And then 1 plus 2 plus 3 plus all the way to 8 is equal to 36. Oh my god, it is 36. So basically we say, is this possible? Oh, it is not possible because we do 8, 7. This is not, this I cannot use, right? This I cannot use because it's a 7, right? It's a 7. I have 1 addition, I have plus 1, but this plus 1 cannot use. Then 6 requires 6. This is a minus 1. 5, 4, 3, I have a minus 1. 2, 1. So I can cancel 1, but yeah, so I cannot use this. I cannot use this. I have to go. So I have to go, which means I don't need to do this, right? This is not necessary. So what I do is from right to left, right, from right to left, require is equal to none to n. No, actually no. Required is equal to mid, right? And from right to left, I say for I in range n minus 1, minus 1, minus 1, right? And what do? I say deficit, right? So we need a, deficit is 0. And what we do is d is equal to usage limit I yeah, whatever I have minus required, right? And if we don't have any deficit, right, we say if d is smaller or equal to 0, then deficit plus equal to d, right? Else, if d is larger, it means we have, and only if deficit is smaller, right, then I can do, oh, what do I say? So D, right? We should say if D is larger, and then we shall do deficit shall equal to deficit plus this, and cannot be more than 0. It cannot be more than 0. Yep. So like else deficit shall equal to deficit shall equal to minimum 0 and deficit plus D, right? This is important. We cannot increase, right, deficit to above 0, because once the deficit is cleared, any extra repeats of the current number cannot count towards the deficit in the subsequent iteration. Right, so we do all that. We don't need this, don't need this, and then we say if deficit is larger, deficit is equal to 0, right? Basically, it's either negative or it's equal to 0. No deficit, that's good. Otherwise, we do this, and then we do this. Okay, let's see. Fail. That is terrible. Well, because I forgot to do one thing. Rec equal to maximum 0 rec minus 1. Yep. And this is the same idea as this one. Right? It's exactly the same. But we can omit, right? We can reduce. We can omit the repeats if they are larger than, they are no smaller, right? If they're no smaller than the max number of groups allowed for the associated number. But other than that, it is the same. It is exactly the same. So that's time saving. I thought I can have some time saving, but yeah, it's not happening. It's not happening. I mean, this might be a little bit time saving. I mean, yeah, it is a time saving, right? We can omit. The omission can reduce the time, can reduce the runtime, because we will decrease. We can, because the total length of usage limits that goes into the binary search will be smaller. maybe smaller, right? Maybe smaller than the original length. But this one overall is still O(n) log n. It's still O(n) log n. And it's the same thing. All right, anyway, so we can try this one. Maybe just by, reducing, we can cause significant decrease in time. I'm not sure. All right, I'm gonna run through this. Let's see if everything still works. Okay, everything still works. Let's hope this one will be slightly faster. And it's the same idea, so it doesn't work. All right, that will be it for my struggle. I will have to read. I mean, we can read the hint, the actual hint. I mean, so far I just check on this. Hint 1, can we solve using sorting and binary search? Sort the array, increasing order and run binary search on the number of groups X. Determine if a value is feasible, greedily distribute the numbers such that each group receives 1, 2, 3 X numbers. Okay, that's my solution. Run binary search. Oh my goodness, this is useless hints. This is as useless as it can be. They just break this into two. Oh god. I mean, I did. This is binary search, but it's slow. It's so slow, which means... Ooh. 7 lines of code. That's 10 lines. 10 lines. I mean, we can combine these into one line. Oh yeah. 2, 3, 4, 5, 6. Oh no, that's not. I was like 4 and 14. No, that's not right. That's, I don't know, there's 18 lines. I have 18 lines of code. But this can be combined. This can be one line, right? How'd you go, sir? Oh my. Oh my. All right. I think we have a lot of things to do. Holy shit. Wait, he says O n. Wait, what is this? Oh, this is O(n) log n. And oh. Okay. All right. So this have to do this tomorrow. Damn it. Damn it. Nah, it's too late. Let's do this tomorrow. Man, look at this. It's so simple, right? It's so simple. And what the hell is a math solution? The inner for loop job will be called exactly in time. I have no idea what this means. Okay. Yeah, we just do it one more time. Do it one more time tomorrow and then try to figure out what this method is. Oh, he added a diagram. Yeah, I was like, this doesn't look like his style, and he doesn't do this often. Usually he just... Oh, and he wrote, oh my god, oh wow. He wrote so much. Yeah. Damn. Nah, I don't think we're done. It's just, this is how this always be. Well, I think binary search, yeah, I think this is an interview. Maybe it's required, but yeah. All right. Oh, hello. I'm not in Seattle. I'm in San Jose, in California. Yeah, binary search is expected. Maybe interview, they will give you hints. Yeah. I mean, interview, if you say it's binary search, it's pretty clear how to think about it. But before that, yeah, struggled. But ON, that's a different story. That's a different story. All right, that will be it.